Step-by-step exam solutions. OK Physics class, training you to excel. Subscribe, like the video, share this video with your friends. Click for alert so that you receive the next presentation. Please drop a comment for a better service. OK Physics class. Present 5 steps to exam success. Step 1, pray. Step 2, plan. Step 3, prepare. Step 4, preview. Step 5, perform. Step-by-step exam solution to simple harmonic motion. We are looking at video number 6, the last video for this presentation. In video number 4, we look at oscillation of simple pendulum. In video number 5, we look at oscillation of a mass attached to the lower end of a spiral spring. In this final presentation, the last video, video number 6, we are looking at types of oscillation and resonance. In this video, we'll be looking at 3 types of oscillation. Number 2, we'll be looking at what is resonance and types of resonance. So these are the things we'll be looking at in this presentation. Number 1, types of oscillation. Number 1 we'll be looking at is what we refer to as free oscillation or free vibration. Look at this vibration or the oscillation of a simple pendulum. You see that the oscillation almost is constant, as if no energy is lost. So free vibration occurs if the total energy of the system of a vibrating object, a vibrating body, remains constant or true. That means no energy is lost. The system do not lose energy to anything. Then if there is no loss of energy, what then is the implication? It means, as it's oscillating here, you see that the amplitude all through is the same. So when an object is undergoing free vibration, the amplitude of vibration, you can see, remains fairly constant. The amplitude of vibration remains fairly constant. And since the energy of the system depends on the distance or displacement from the rest position, and amplitude is the maximum displacement from the rest position. So if the amplitude is constant, it then means that the energy or the vibrating object is constant. So in that case, we see the first condition that the amplitude will remain fairly constant, while also the period of oscillation also remain fairly constant. So now, that is what we see when an object is undergoing free vibration. Now, for free vibration, as I said, both amplitude and the period of oscillation remains constant throughout the oscillation. The period of oscillation, distance from here to here, or from this end to this end, will remain constant all through the vibration. The amplitude will remain constant all through the vibration. So when we have a situation of an object vibrating so that the energy remains constant, implying that the amplitude of oscillation remains constant and the period of oscillation remains constant all through the vibration. Such an oscillation, such a vibration is known as a free vibration or oscillation. It's very difficult to get in nature, but the oscillation of a simple pendulum can be approximated to a free vibration because it vibrates for a very long time. The oscillation of a spiral spring, when the force constant is very weak, can also be approximated to that, in theory at least. So we're now going to move to the next one. Forced vibration or oscillation. As the name implies, it means the vibration is kept by application of an external force. So now look at this. As the spring vibrates, it vibrates from the maximum upward displacement to the maximum lower displacement. And the squeezing of the spring and the stretching of the spring is what sustains the vibration. So in this case, even though the energy appears to be lost during the vibration, the external force applied to the system supplies the force, supplies external force, supply an external energy to keep the amplitude and the period of oscillation fairly constant. So now for a force vibration, you see that happens when an external periodic force constantly replaces energy lost by the vibrating body. That happens when an external periodic force constantly replaces energy lost by a vibrating object. So when that happens, we have what we refer to as force oscillation or force vibration. Now, examples of force vibration are vibration of what? The piston of a car. The piston of a car, examples of force vibration. Number one, vibration of the piston of a car. So you see that the piston of the car is keep on vibrating as long as the engine is on. So now the power and the levers of the engine keeps the piston in that up and down movement, to and from movement. So therefore, that oscillation of the piston is a force vibration. If you stop the engine, the piston will stop vibrating. The number two, vibration of air column in pipe when a sounding tuning fork is placed over it. So when you strike a tuning fork and place it over a pipe with water inside, and there is air over the water, you discover that the air will vibrate and resonance and produce very loud sound. If you remove the sounding tuning fork, the sound would fade. That shows that the sound is coming as a result of the vibrating tuning fork. So now the vibrating tuning fork makes the air column above the water to vibrate. The vibration of the air column above the water to produce loud sound is an example of force vibration. So we have seen number one, free vibration, amplitude and a period of oscillation remain constant naturally. Then we have seen number two, force vibration, amplitude also and the period of oscillation remains constant, but the energy lost is being replaced by an external force. Number three, we look at damped oscillation. Please subscribe, like, share the video, click for notification for the next video. So now, damped or vibration or oscillation. Vibrating object loses energy gradually until they stop. Most objects in nature may not actually vibrate for a very long time. They keep losing energy, even the simple pendulum. And after some time, they will come to a stop. So when an object vibrates and continues to lose energy, such vibration is said to be damped. So damped vibration happens if energy is continuously lost as the body vibrates. So if that happens, the energy is continuously lost. So now look at here, we have just an example. This first one here can be approximated to a free or force vibration where the amplitude, the black sine curve, is fairly constant. The blue one is damped because after some time it slows down. And what happens when it slows down? The amplitude keeps decreasing. The amplitude keeps decreasing until the amplitude almost becomes zero. So that means the vibration is damped when it loses energy continuously until it stops. It stops when the amplitude becomes almost zero. So now the graph for damped oscillation looks like this. You see that the period of oscillation keep decreasing, and also the amplitude keep decreasing with time. So here you say the amplitude and the period of oscillation decreases due to energy loss as the body vibrates. So now this gives us the three types of oscillations: free vibration oscillation, forced vibration oscillation, and then number three, damped vibration or oscillation. So now let's move to the next concept, natural frequency. Now, most objects will have a frequency they will, under normal condition, they will tend to vibrate and remain in that vibration for a very long time. Such frequency an object tends to vibrate for a very long time is referred to as its natural frequency. So the frequency with which a body vibrates, which a body tends to vibrate when left undisturbed, is the natural frequency. Is the natural frequency. That's the normal frequency. The frequency it will tend to vibrate for a very long time undisturbed. So when a body vibrates at natural frequency, what are the things we'll be expecting if a body is vibrating at natural frequency? Number one, you see that the amplitude, the velocity, the kinetic energy will all be what? Maximum. An object vibrating at its natural frequency will have maximum amplitude, maximum velocity, and maximum kinetic energy. Since all these are maximum, then it means that the energy also, you can see the kinetic energy is also maximum. Meaning, if an object is forced to vibrate at its natural frequency, it may lead to damage, it may lead to collapsing of a bridge, it will lead to a glass cup breaking and getting shattered because it is forced to vibrate at its natural frequency. So now, we'll now go to the next concept along with natural frequency, and that is resonance. What do we mean by resonance? So a resonance is a concept in physics that comes in when an object is made to vibrate at its natural frequency. Remember the natural frequency. The normal frequency, the object will tend to vibrate for a very long time. If an object receives external force, a vibration outside itself, and then that vibration outside itself makes it to vibrate at its natural frequency, in that case, we say that resonance has occurred. So therefore, we can say that resonance is a phenomenon which occurs when a body or a system is made to vibrate at its own natural frequency. Why? Because of the energy it receives from another body or system which is vibrating with the same frequency. So the one vibrating with a particular frequency forces another object to vibrate at its own natural frequency. Then resonance takes place. Like I said, whenever that happens, it can cause a lot of disruptions. So now, types of resonance. Number one, we look at electrical resonance. Electrical resonance happens in a radio and TV circuits, radio set and TV set circuits. This radio set and TV set produce largest maximum response corresponding to the frequency of a particular station when the inductive reactance, remember there is an inductor, there is a capacitor. The inductor produces a resistance, a reactance to the flow of current. The capacitor produces a reactance to the flow of current. The inductive reactance now and the capacitive reactance at a point where they become equal. That means the inductive reactance becomes equal to the what? Capacitive reactance. The electrical resonance will take place. So that's the first type of resonance we have, electrical resonance. Then number two, we're going to be looking at will be mechanical resonance. This occurs when a mechanical system is caused to vibrate at its natural frequency. For example, When soldiers are marching in steps, left, right, and they are marching in step, because of that phrase, marching in steps, they can force the bridge to vibrate at its natural frequency. And when that happens, the bridge will vibrate with its maximum amplitude and also maximum kinetic energy. That if the soldiers were not forced to break their march, that bridge will collapse. That is a mechanical resonance. Then the next one we also have is a resonance in sound. For example, we talk about the tuning fork. In sound, resonance occurs when the air column trapped in a tube vibrates at its natural frequency, producing prolonged audible sound. The example is the case of what? A tuning fork, vibrating tuning fork placed over air column, so that the air is now forced to vibrate at its natural frequency, giving us a large sound because the amplitude is at maximum. It gives us a large sound. So therefore, that gives us sound resonance. So for resonance, remember we have number one, electrical resonance, happening in a tuning circuit of TV and radio sets. Then you have mechanical resonance. Example is soldiers marching across a bridge. For example, if an old car is moving at a very high speed, the engine of the car can force the glass inside the glass of the door to reach its maximum amplitude and frequency, vibrate at natural frequency, that the glass will start making noise. That is also a mechanical resonance. Also, you have a sound resonance that happens in air, that makes air column to vibrate at the maximum amplitude. That happens in what we call these musical instruments that use air to work. So that gives us resonance in sound. That brings us to the end of this presentation. Please remember to subscribe, like the video, share the video, and click for notification so that when the next video is released, you will receive it. Thanks for watching.